Electricity. Elemental power. Since the dawn of time, people have dreamed of giving life to inanimate objects. So if your Christmas present comes without batteries, what you need is a continuous supply of electricity. Lightning is deadly. Even if he could catch it, it'd all be over in a flash. What he needs is a generator. This one produces enough electricity to make your hair stand on end. Static electricity. So all he gets is a short, sharp shock. Could a bike dynamo be the answer? So long as he keeps pedalling, there's a continuous supply of electricity. All he's got to do is complete the circuit and turn on the power. He's done it! So, with a pair of scientific eyes, where else would you look for complete electrical circuits? Dodgems run on electricity, so where's the circuit here? And what are the components? There's a power supply, a main switch, and a switch in the car. How does the electricity get into the car? And after it's been through the motor, how does it get out again? To show how it gets in and out, what you need is a diagram. Shift everything into a rectangle and you've got a circuit diagram. What about the diagram for this circuit? It's the wire filament that produces the light. And for that to happen, electricity has to get in and out. So how many wires are connected to the lamp? Blue is neutral, brown is live, and the switch breaks the live wire. Now you can draw the diagram for the whole circuit. Remember the bike dynamo? There's only one wire coming out of it. And there's only one wire going to the tail lamp. So how's the circuit completed? How does electricity get into a model engine? The motor's connected to the wheels. This is the power supply. So how is the circuit completed? This circuit tester shows the power comes in through one rail and goes back through the other. Real railways need much more electricity. It's supplied through power lines high overhead. One reason for this is that electricity can be conducted by living things. Grass is always greener on the other side. But what if it's an electric fence? No, don't do it! So how was the circuit completed? Farmers use electric fences to keep sheep or cows in one half of a field. The power supply is connected to the wire. And this giant metal corkscrew goes into the earth. So the circuit seems to go from the fence to the power supply and then to the earth. But that's only half the circuit. So how does it get completed? When an animal makes the connection between the earth and the wire, the circuit's completed and electricity can flow. So the earth must be an electrical conductor. High-tension wires carry a massive amount of electricity. Make sure that you don't complete a circuit between a power line and earth. Thunderstorms are dangerous too. That's why tall buildings need lightning conductors. A wire runs all the way down from the top of the spire, so if lightning strikes, there's a direct connection to Earth. And an earth wire's what you need for protection whenever you use the mains. For safety, the wiring in all buildings needs to be connected to, and earth wires are always green and yellow. The earth connection is a steel plate which is buried in the ground. The wire from the earth plate is connected to the sockets inside all the buildings nearby. They're all supplied from an electricity substation. But for earthing to work, you've got to get your wiring right. Which wire's which, and what goes where? How does the earth wire protect you? And why is the fuse important? It's easy to see what electricity can do, but you can't see electricity itself. What's going on inside the wire? This is a model. They're doing circuit training, and their circuit represents an electrical circuit. What they're doing is eating squares of chocolate and then going on to do various exercises. Lifting a bucket, skipping, and riding a bike. So how does this circuit represent the other? The battery is the supply of chocolate, and the different exercises are like the components of the circuit. They each need energy to keep them going. And the chocolate supplies the energy. So what are the humans? They carry the energy around the circuit, just like the electric current. Back at the battery, they top up with a fresh supply of energy for the next trip round. We all know what happens when the current is switched off. But what happens when you put in a second battery? What will change if twice as much energy is available? If their model's any good, everything in the real circuit should go faster too. So how good is this model? Does it help you understand what's going on inside the wire? And can you think of a better model? A different way of explaining what happens in an electric circuit? To find your way around a circuit in the hills, what you need is a compass. They always point north. You could make do with a magnetised paperclip and a cup of water. Which way will the paperclip point? It lines up north-south along the Earth's magnetic field. You can use a compass to show that an electric current makes its own magnetic field. This compass is inside a coil of wire attached to a power supply. Switch on the current and the coil behaves like a magnet. Wind a coil round an iron nail and what you get is an electromagnet. They're seeing which one will hold the most paper clips. Does the shape of the nail make any difference? What about the number of turns in the wire? The nail is magnetic only when the current is switched on, which means an electromagnet can be switched off. When might this be useful? Switch on this circuit and the electromagnet attracts the steel plunger. Switch off and the magnetism disappears. To make a bell, just add the chimes. Really important bells rely on a make and break circuit. The important parts of the bell are an electromagnet and a springy striker. The circuit's completed with a battery and a switch. What makes the bell keep on ringing as long as you keep your finger on the button? Why do you think it's called a make and break circuit? And how else do you get movement by using electricity and magnetism?